In this part of the course, we're going to talk about induction and recursion. But before we get to those, we are going to describe what sequences and series are because they are a component of both induction and recursion. So informally, the word sequence in mathematics is the way that you perceive it in everyday life as well. It's a series of numbers written in a row. We generally write them in this form, A1, A2, A3, and so on, where the ... in the middle represents that we've skipped some parts of that sequence. Each member of the sequence is called a term. So for example, A3 here is called a term. The subscript that denotes its location within the sequence is called the index. So the index is going to be 3. Now, some sequences are finite and some sequences are infinite. And so we take care to actually point out what kinds of patterns there are. If the sequence is finite, we can finish writing all of the terms and we won't have this ... appearing anywhere if we can actually write it out shortly. If the sequence is finite but very long, we might wish to ... to represent that we're skipping some steps, but the sequence is still going to be finite. Infinite sequences are the ones that go on forever. So for example, 1, 2, 3, 4, ... with no last term, indicating that this pattern will go on forever. Now you do have to be careful in not abusing the ... notation and only using it after you've provided sufficient terms to indicate what the actual pattern is. Because if I just write 1, 2, ... then it's not clear what the pattern for the ... is. Is it 1, 2, 3, 4, 5, and so on? Or maybe it's powers of 2, or maybe it's something else altogether. The terms that you do include have to be representative of the sequence, and you have to include enough of them, often 2 is not enough, in order to indicate what pattern you're actually following. Now, because we don't always want to write out all the terms one by one explicitly, we're going to use an explicit or general formula for the sequence that will be a rule that shows how the sequence is formed without providing implicit term one by one. So here we're going to say a sub k is going to be some function of k, where k represents the index. So as the index changes through the sequence, the term will follow some kind of pattern that has been recorded by this general formula. In order to see how that works, let's take a look at this example. Write out the first 5 terms of each of these sequences. So the first 5 terms, 1, 2, 3, 4, 5, right? Let me, because this is our first example, actually write them out as terms at first. 1, 2, 3, 4, and 5. So again, the indices are going to be represented here by k. So the first term has to follow the rule corresponding to the first index. So if A1 is going to be computed, I have to submit 1 into k, so I'm going to get 1 over 1. For the second term, the index is 2, so my k is 2, which means that I substitute 2 for k, and I'm going to get 1 over 2. Next up, A3, I substitute 3 for k, and I'm going to get 1/3, 1/4, 1/5. Once you get familiar with the notation, you no longer have to include A1 through A5. You can go directly to the numbers. So let's see what happens here. Here, let me actually just order them by the values of k. So 0, 1, well, sorry, not 0. We start at 1, 1, 2, 3, 4, 5. So when k is 1, which means that we're after the first term, A1, I'm going to have -1 to power 1. When k is 2, I'm going to have -1 to power 2. When k is 3, -1 to power 3, and so on. Now notice that, of course, I can simplify these numbers, and I will probably notice what the pattern for this sequence is a little bit better, but it's probably not going to be your first step, and certainly not in your first example. But once we do this, let's actually try to simplify this sequence. So -1 to power 1 is -1. -1 to power 2, anything to even power becomes positive, so this is going to be just 1. -1 to power 3 will remain negative, negative 1 to the power 4 will become positive, and so on and so forth. So I can see that this is a 1, negative 1 alternating sequence. And we're actually going to use this form a lot to help us when we want to alternate the positive and the negative signs. I'm going to leave the other two questions for you to do. I'm only going to notice that I strongly encourage you, at least in the beginning, and almost certainly at many points in the future, to not just jump directly to the simplified form, because the simplified form loses the actual artifacts of the pattern. Here I can see that -1 stays the same, but the power changes. Whereas once I've simplified the terms, I can no longer see that as clearly. So you will notice if you go through this example, what happens there. Don't simplify it first so that you can leave the pattern as very obvious, and then you can simplify if you need to actually work with the terms directly. Next up, we're going to move in the opposite direction. I'm going to give you a sequence, and I would like to find an explicit formula for it. So going from the sequence to the general term. So what are the patterns for these sequences? I have 2, 4, 8, 16. So it looks like every time I'm multiplying by 2, and having worked with powers of 2 before, I can see that this is 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, and so on. So my first term, corresponding to k equals 1, is 2 to the power 1. My second term that corresponds to k to the power 2 is, k equals to 2, is 2 to the power 2. And so on. So it looks like if I set AK to be 2 to the power k, I am going to be in good hands here. Okay? It's always a good idea to double check it yourself. So now if I plug in k equals 1 for A1, I'm going to get 2 to the power 1. Correct. And then 2 to the power 2. Correct. And so on. This kind of check is going to be particularly important once we get into the alternating series, just to make sure you have it right, whether you're starting with minus or you've accidentally started with a plus and then started alternating later. What's happening here? It looks like I have the exact same sequence, but I'm not starting at 2, I'm starting at one term above. So I'm going to have 2 squared, 2 cubed, 2 to the power 4, 2 to the power 5, and so on. So what that means now is that my first term that corresponds to k equals 1 actually has 2 in the numerator, in the power. My term that corresponds to k equals 2 has 3 in the power. The term that corresponds to k equals 3 has 4 in the power. So it looks like the power is always 1 more than the actual index. So it looks like if all I do is raise the power by 1, I'm going to be in good hands here. And again, once you've decided on what your formula is, it's a good idea to double check it. So if I plug in k equals 1 now, I'm going to get 2 to the power 1 plus 1, which is 2. Good news. If I compute A2 and substitute 2 for k, I'm going to get 2 to the power 3, which is the second term here. So that's also good news. Okay, so this looks like it's working just fine. Now we have this plus minus alternation happening. But the terms themselves, the numbers themselves, are exactly the same as in part A of this example. So it looks like I'm able to keep the exact same format, except now I have to also be able to go minus, plus, and so on. So this is where my -1 to some power will come in handy. And I generally actually prefer to more or less guess the power as just k, and then adjust it if necessary. So if this is my initial guess, and I'm going to sub in 1 for k, what am I going to get? Am I going to get the proper term, or am I going to be wrong in the sign? So I have 2 to the power 1 and -1 to the power 1. -1 to the power 1 is going to remain negative, so I'm going to get -2. That's excellent news here. Okay, so it looks like this is exactly what it's going to be. Let's take a look at this one here. There looks like there is a numerator and denominator. There is the signs. There is a lot of stuff going on. So a lot of these times, you're going to have to stare at a sequence for a while in order to actually figure out what the pattern is. But because these examples all had 2, 4, 8, 16, I can actually see that that's part of the numerator. So it looks like what I have on top is 2 to the power k. Except for, notice that I'm starting with 1. So when k is 1, I want to actually have 0th power of 2, not the first one. So I'm going to subtract 1 from k in this power here. Okay, I'm going to finish building my function and then figure out if I'm actually correct or not. What do I have on the bottom here? 2, 3, 4, 5, and so on. Well, if I write this 1 as 1 over 1, then I can see that I, in fact, have 1, 2, 3, 4, 5, which is a very nice sequence. It's just a sequence of indices, so I'm just dividing by k over here. Okay, so I have this exact same sequence, except for now I've had to downgrade the power by 1, kind of exactly opposite of what we did in part B. I have just k on the bottom, and the only thing that I have yet to attend to is the fact that there is a minus in front of every other term. So again, it's going to be minus 1 to some power. And let's see, if I put in k, is that going to work? Is my alternation going to start with the proper one? So if k is equal to 1, then I have minus 1 to power 1, which is negative, but my first term is positive. So in this case, I have to adjust my power somehow. And the adjustment is very easy. All you have to do is either add or subtract a 1. So let's say I'm going to add 1 here, because that changes from even to odd in the actual power, and now that should work out. So just as a final check, I'm actually going to check all of the components all together. So if I sub in k equals 1, 1 everywhere for k, am I going to get 1 as the answer? I have 2 to power 0, so 1 divided by 1, which is good. And then I have negative 1 to power 2, which is going to be positive. So all good news all around. You can plug in k equals 2 as well in order to check the next term in parts to see if it actually works out. As I mentioned before, notice here, for example, that when I was writing this out, I did not simplify 2 over 2 to be 1 because I did want the pattern of the powers of 2 on the top and just the indices on the bottom to be obvious. If I've simplified this to be 1, it would not be clear how we got from 1 to negative 1 to 4/3, and then this would have been substituted by 2 and so on, right? So keeping unsimplified terms allows you to see the patterns better. Now, once we have sequences are just lists of numbers. The next thing we can do is propose an operation on those sequences of numbers. And in particular, we will be interested in computing the sum of these sequences. So if I have some kind of sequence, the sum of its first n terms is going to look like this. Nothing special, right? But because we will be working with these sums quite a bit, we would like to introduce a notation that's going to create a shortcut and will allow us to work with them more efficiently and more directly. So the notation is a little bit bulky, but we will go through it one piece at a time so that it's clear where it comes from. The notation has this big symbol that's called a sigma, and the way that we read it, this simply represents the actual summation. This means that what I have are the pluses all over the place. What goes inside the sigma is my actual representative term. So we've been using a k here. I'm going to use a I here. It doesn't really matter what you call your index. Normally we call it I for I index. So this just means so far that I'm adding up the AI terms. Now, I'm adding up a bunch of terms, but next I need to specify what am I starting at and where am I finishing my sum. So that's what's going to go on the bottom of the sequence. I'm going to say that my initial index that I'm starting with is 1. So this is my start index. And then I can indicate that I'm only interested to go up to index n, which is what's going to go on the bottom, on the top, and this will represent the final or the last index. Okay, so this is the notation that we're going to take throughout. We're going to have the sum, so that represents the fact that I'm adding everything up. I'm adding up terms that look like AIs, where I start with index 1 and end with index n. Let's see how this works with a particular example. So let's say here is our first sum. So again, summation represents that I'm going to be adding a bunch of stuff all together, and I'm going to be going through indices starting from 1 to 5. So because it's our first example, I'm going to write this out very explicitly. I'm going to run through all the indices from 1 to 5, because that is what my notation here stands for, from 1 all the way up to 5. And the sum means whatever those terms are equal to, I'm going to be adding all of the results up. Now, what are those terms actually equal to? This is the general form of the term that I'm adding. So when I is equal to 1, I'm going to plug it into here and compute it. If I is 1, what I get here is 1 squared. When I is 2, I plug 2 into my general term and I get 2 squared. When I is 3, I plug that into my general term and I get 3 squared, 4 squared, and 5 squared. And we're done. Now, as you practice more and more, you won't have to write out this line, but I find that in the beginning, it's very useful to keep track of what you're actually doing. So let's take a look at this next sum. Maybe pause the video and try to see if you can write this out by yourself, and then come back to see what we do together. Okay, so as I suggested, it might be a good idea to first look at the actual indices. So here we go from 0 all the way to 7. 3, 4, 5, 6, 7. Perfect. Okay, the sum, the big sigma, indicates that whatever I get, I am going to be adding it all up. And next, I'm actually going to substitute the indices into the explicit formula. So when I is 0, I plug it into here, I get -1 to power 0. When I is 1, I get -1 to power 1, and I can see that all I need to do is actually write them out as powers and hope that it fits on the page. There we go. Once again, obviously, I can now simplify this expression because I can figure out what the powers are, and then I can actually perform the addition. Similarly here, once I write it out this way, I can actually calculate the final answer. But for now, I'm interested in how to expand the sum and what it represents, rather than the actual final number that it stands for. Let's take a look at a few more examples of summations, some of which are pretty easy and the other ones are going to be a little more intricate. So here I have, going from 0 to 5, the sum of cubes. So thinking that you guys have practiced the previous two examples already on your own, I'm going to skip the phase where I write out all of the possible indices and then fill it out, and start actually filling them in as I go. So it goes from 0 to 5, and I'm going to take that index and cube it. So 0 cubed plus 1 cubed plus 2 cubed, 3 cubed, 4 cubed, and 5 cubed. Excellent. Next up, we have this. The indices go from 3 to 6 into this formula. So when k is equal to 3, I'm going to have 3 divided by 3 plus 1. Next up, I'm having to go from 3 to 6. So next up is k equals 4. 4 divided by 4 plus 1. Next, k is 5. And finally, k is 6. Okay, seems pretty straightforward. The thing to remember is to be careful because indices do change every time. So you cannot just assume that everything will always be starting from 0 or from 1. And you also have to make sure that you actually put the corresponding index in properly. Let's take a look at this one next. So what I have here is k's going from 2 to 5, but what's inside my sum is independent of k. So this case is a little bit tricky to think about at first, so let me go back to writing out what I have for my indices, and I know that I'm going to connect it with a plus. So from 2 to 5, here are all of my possible index choices from 2 to 5, and now I'm going to have to plug those indices into the actual explicit term. So when k is equal to 2, the general term is equal to 3. There's no k here, so it's just 3. When k is equal to 3 and I plug it in here, there's nowhere to plug it in, so by default it's just 3. When k is equal to 4, the same thing, and when k is equal to 5, also the same thing. So what we notice is if I have a constant inside the sum that does not depend on k, I don't have to plug anything. I simply write out that number, that constant, out as many times as there are integers between 2 and 5. And now this might also be reminiscent of, remember we calculated how many integers there are between m and some number n? These types of things is where that formula for the number of integers in a list will also come in handy. Let's take a look at this one. So what I have is I is from 3 to 3. So between 3 and 3, there's only one index, which is 3 itself. So I only have one term here, 3 minus 1, 3 plus 1. And that's okay. No one says that a sum has to have any more terms than any specific number. Let's take a look at this sum. So this is going from 1 to n. So this is a more general summation. I don't have a very specific numerical final term. I have n, so some number n of steps into the future. But I know that I'm starting at 1. So let's write out what this term will look like for 1. If I plug in I equals 1, I'm going to get square root of 2 minus square root of 1. So this is for I equals 1. What's going to happen when I have I equals 2? So I plug 2 in here. I'm going to get root 3 minus root 2. So notice that I'm simplifying, but barely. I'm just doing the plus 1 addition, but I'm not even attempting to simplify the actual square roots. And we will see in a moment why that's the case. Okay, let me write down one more. So I equals 3. If I plug in 3 here, I get square root of 4 minus square root of 3, and that corresponds to I equals 3. Let's say I carry on for quite some time up until I hit my index n. So my last case here will be I equals n. So I'm plugging in n in for I. What am I going to get? I'm going to get square root of n plus 1, not like I can simplify that, minus the square root of n. Now, the reason I wrote out this sum this way is because now I can actually spot the pattern not within each of the terms themselves, but in their totality. So look, here I have root 2, and here I have negative root 2. Here I have root 3, and here I have negative root 3. And by the way that the sum is going, I know that the next term here will have a negative root 4. So what I am noticing is that all of these middle terms will cancel each other out. This will cancel each other out with something that's upcoming. Now, will this negative root of 1 ever get canceled with anything? Well, no, because everything after this is actually increasing. So this is the smallest thing I'm ever going to see. So this is not going anywhere. Now, let's look at our last term. What's going to happen here? Am I ever going to see square root of n plus 1 anywhere in the previous stages? No, for the same logic. Everything here is increasing, and this is the largest thing I've seen so far. What about minus root n? Would I have seen that anywhere previously? And you can think of how we've matched the pattern here. The second term in each of these pieces here have that appeared somewhere before. And you can see that it appeared in the previous index expansion. So this minus root n would have actually appeared in the previous step with the positive sign. So this would have canceled with something right before its time. And the only terms I will have left will be minus root 1 and square root of n plus 1. This entire sum has collapsed into something really small. This is why these types of summations are called telescoping sums, because we start off with something that we can collapse into a very small expression, like the telescope, right? Like we build parts of the telescope and then we simply squish it together and we get something from the very beginning and something from the very end. And that is going to be our final computation. The really nice thing about something like this is, now if I tell you, compute this sum for n equals 7, you don't have to go through all of this work. What you have to do now is simply plug 7 into the final formula and get your final answer. This is why general summation simplifications are really powerful, because once you've simplified it once for a general value of n, you can apply it to any other value of n. We're now going to practice a little bit more with actually using summation notation and writing out sums with it. I strongly encourage you to pause the video and try this question for yourself. So what I would like here is a sum, I equals something to something else, and some kind of term in the middle that actually represents this summation. This is excellent practice for using the notation, so take a moment to do so. I'm going to live in blissful ignorance, thinking that you guys have actually taken the time to go through these examples by yourself, and let's see how this works out. So I have 2, 4, 8, 16. Notice that this is the exact same sequence as we've already seen on the previous page, which means that we've already identified its general term. And that is usually the hardest part of the problem, figuring out what the general term is, and then simply assigning the initial and the final index in order to compose the sum out of it. So the general term is 2 to the k. So then I already know that I have a sum of powers of 2, so 2 to the k. Now all I have to figure out is what is my first and my last index here that the sum actually goes to and from. Well, the first term I have here is 2 to power 1, so my starting index will be 1, and the final index isn't really present, it goes on forever, it's infinite sum, so my final index will be replaced by infinity to indicate the fact that this just keeps on going. Similarly, I have this thing right here. These are still powers of 2, so I can still use the exact same general term, but now I am not starting at 2 to power 1, I am actually starting further down the sum. So this 16 is 2 to power 4, and I can adjust that by changing my starting index. So here I'm going to start with 4 and go on forever. Next up, I have this. So there's a couple of different ways to view this. One of them is to notice that the pattern is that it's always 3 multiplied by a higher number. It's 3 times 1, and then it's 3 times 2, and then it's 3 times 3, 3 times 4, and so on. So what I have is 3 times the index, where the index goes from 1 to infinity. Okay, so I can see the 1, 2, 3, 4 as my index sublist, and then everything is just getting multiplied by 3. The other way to actually see the sum is to simplify it a little bit at first. So the one other thing I can do here is I can factor 3 out from the original sum, and notice that what I get is 1 plus 2 plus 3 and so on, in which case the way that I would write this sum would be 3 multiplied, so there's this 3, and then there's this sum, which is just the indices themselves that go from 1 to infinity. So this 3 can appear inside or the outside because of the summation, and in fact we will later derive the rules to show that constants can in fact be taken outside of the summation. Next up we have this thing here. So what do I have? It looks like on top I have 2, 3, 4, 5 and so on, and on the bottom I have the same sequence but starting a little bit later, 4, 5, 6 and so on. So it's going to be some kind of a sum where I have the index divided by the index plus 2, because you notice that the difference between top and bottom is always 2. Now I just again have to decide what is my very first term, where does it start at? And so in this case, let me just write this out. I notice that my first term has 2 as the top, so that would correspond to my index I being 2 on the top. And again, this goes on forever, so I'm going to go all the way up to infinity. Next up is this guy. So here I have 1, 2, 3, 4, 5, 6, and so on. So just the indices, kind of like the same thing as we've seen here, except for their signs go from plus to minus. So I know it's going to be -1 to some degree. Let's wait, I'm not going to fill this out quite yet, multiplied by the index. Now, because the index actually starts, the first term here is 1, I have to go from 1 to infinity. And now based on that, I'm going to figure out what the power here should be. And my choices essentially are, should it be I or should it be I plus 1 in order to match the actual pattern of pluses and minuses. And here, the easiest way to do it is simply by trial and error. If I plug in I itself, I'm just going to have to check the first term. So when I is equal to 1, I'm going to have -1 to power 1 times 1, which would be -1, which I do not have, which means that this is not the right choice. So let me try I plus 1, which is now at this point almost guaranteed to be correct. So what I have now, if I plug in I equals 1, I have minus 1 to power 2 times 1, which will be positive 1. So I'm in good hands here. This example is quite similar, but a little bit more complicated in terms of noticing the pattern on the bottom. So notice that the pattern on the top is 1, 2, 3, 4, and so on. So the same index I, except for now the pluses and minuses occur in exactly the opposite way here. So here is where I know I'm going to have minus 1 to power I times I, because that's exactly what didn't work last time. But now what about the bottom? I should also point out that I'm going from 1 to infinity, right? What about the bottom? How do I get this 3, 5, 7, 9, and so on? So it looks like all I'm going through are odd numbers. And the way that odd numbers can be written out is it's an even number plus 1 or an even number minus 1. And so I simply have to decide which one of these forms matches my index going from 1. And again, the easiest thing to do is try it by trial and error. Try 2i plus 1, and in this case, that's the one that's going to work out. So if that's the one that you tried out first, that's the one you stick with. I know I should point out that dealing with sums generally takes a lot of practice. And the hardest part, and the part that everybody I think likes the least about sums, is particularly these types of exercises, where you have to rely on being able to transform a pattern into an explicit formula. Just like anything else, this simply needs to be practiced over and over again. Next up, we're going to take a look at how we can actually deal with the summation and why this notation has its pros and cons. So we're calling it massaging the sums because we're going to either separate the terms or blend them right back in. Think of that as kind of like working with a dough. You can take pieces of it out or you can blend pieces of it back in together. We're going to take a look at this summation from 0 to n of j cubed. So this is like the exact same one that we've seen up here, except for I am not going to stop at 5. I'm going to carry on all the way to n. So what I would like to do is to rewrite it by separating the first term. So the sum itself, if you think about this, is 0 cubed plus 1 cubed plus 2 cubed plus 3 cubed and so on and so forth. But I don't want to rewrite it all entirely in terms. I just want to separate its very first term, but keep the rest of it as a summation. Okay? So what we're going to do is write out the first term, which is 0 cubed, and the rest of it has to stay as the sum. Now, the general term hasn't changed. It's still j cubed. But now instead of starting with 0, because I've taken that term out, I'm going to start with 1 and go all the way up to n. Okay, so adjusting for the first term simply means plugging in the number into the inside of the sum, computing this term, and then starting your index at the next number. We can also do the same with the last term. We can separate the last term out. So in that case, I'm not going to change the beginning sum, but I'm going to adjust my last term to, instead of n, to stop at n minus 1. But now I have to explicitly write out what the last term is because I still need to account for it. So if I plug n into here, I'm going to get n cubed. That would have been my last term. So my sum can also be written out like this. We will see later on how this is actually useful. Rewrite using the change of variables. So generally, it doesn't matter what you call your index. So you want to prefer I or J or K or any other letter of the alphabet, it's fine. But sometimes it's actually useful to have different change of indices. So not just J equals K and just relabeling it, but rather actually quantitatively changing some of it. So my index K here goes from 0 to n, but I would like to change it to be the sum in terms of this new j that actually corresponds to k plus 1. So what I'm going to do is transform the first and the last terms or indices here in order to go from k to j. So my first term was k equals 0. So when k equals 0, I need to figure out what my new index j will be. If k is 0, then 0 plus 1, j is going to be equal to 1. And for my final term, k was equal to n in this scenario. So now I have to plug n into here, and j is going to be equal to n plus 1. So this already allows me to change the indices on the summation itself. And next up, I'm going to have to change the inside to not be in terms of k, but rather to be in terms of my new variable j. So I have k plus 1 here, and I have k plus 1 here, which is just actually equal to j. So instead of 1 over k plus 1, I have 1 over j. And this is why it's sometimes nice to use different indices or different variables, because this internal expression now looks a little bit simpler than this one, although that was at the sacrifice of making the final index a little bit more complicated. So recall that we started this lecture with introducing sequences, and then we strung them together with the summation. Another way to put the sequence together is using a product, and the notation is going to be very, very similar to that of the summation. For product, we have a very large letter, Greek letter pi, so this represents the fact that now instead of the summation, we will be putting everything together with the product, but then the rest of it is basically the same. So I have the general term ak, and then I list my beginning and my end terms. So this is my start index, and this is my last index here. Now let's see how this actually works with how we can expand those products out. So again, the notation is very, very similar, except for we're going to replace our pluses in the sum with the multiplications in the product. So what I have here is, if I am going through the indices, I'm going to start with 1 and end with 5. So for my first index, when I is equal to 1, I have 1 squared. And then I'm going to multiply everything I write down together. For index 2, I'm going to have 2 squared. For index 3, 3 squared, 4 squared, and 5 squared. Okay, and again, if I wish, I can actually compute this as a number, and that will be the answer to this. For this one, the same way, I start with 0, I end with 7, and I replace my index with that. So minus 1 to power 0 times minus 1 to power 2, minus 1 to power 3, 4, 5, 6, and 7. Okay, and I can multiply all of these together, and I can already see it's going to be either plus or minus 1, because everything is a plus or minus 1. So it's really just a matter of parity here. Now, while the notation is the same, the actual properties of summations and products are quite different. So let's go through a few very general properties to see how they work. First of all, if I have two different sums, so the insides of them are different, but the starting and the ending coefficients or terms, indices, are the same, then I can actually put this sum together into one. Okay, so I can sort of glue these sums together, but only if the beginning and the end terms are the same. I can do the exact same thing with the product. So as long as the beginning and the final terms are the same, I can put the products together. As we've already seen, if I have a constant inside the sum, I can pop it to be outside of the summation itself. And we've already seen one example with the constant and nothing else in the summation. Let's see how we can do so in general. So this is just saying that for all the indices between m and n, I'm going to add c to itself. So it's going to be c for index m, and then c for index m plus 1, all the way up, c up until the index n. So using our handy-dandy formula for the number of integers between n and m, I can see that this is going to repeat itself n minus m plus 1 times. So I can, of course, then simplify that and write down that this is c multiplied by itself n minus m plus 1 times. Now for the product, if I have the exact same setup, I'm going to be replacing these pluses with the times, but the number of c's doesn't actually change. So this still happens n minus m plus 1 times, but it's a multiplication, which means that now this number will appear in the actual power. Excellent. Let's see how we can use these rules and our already decent familiarity with the summations to simplify the following expressions. So what do I have here? I have two summations. The things inside are different, but the beginning and the last terms are the same, which means, according to this rule, I can put them together. Notice that the minus or the plus, that doesn't really matter. So this rule applies the exact same to the difference as it does to the sum. So what I can do then is have, it's going to be the sum with their common beginning index and their common final index of 7j cubed minus j cubed. Now, I can simplify this further still, right? Because, well, 7j cubed minus j cubed, that's just doing similar terms. So this is from 0 to 5 of 6j cubed. Excellent. Notice there was actually another way to simplify this sum. Instead of applying this first law here, I could have applied the second one right here to the coefficient of 7. So let's see how that would have worked out. So another way to simplify this sum would have been as following. I could take 7 out from the first summation. So then I have from 0 to 5 of j cubed. And then I will leave the second summation b as is. Now we're going to actually have to sort of squint a little bit to notice the pattern. So look, I have 7 of something minus that something. So 7 apples minus an apple. 7 apples minus an apple is 6 apples. It's just my apples are here very, very large. So it's going to be 6 of the same summation. And in the end, my answers actually match up until, modulo taking the 6 out of the summation. So whichever way you prefer, you notice that you've managed to simplify an expression that included 2 sums down to an expression that includes only 1. So there's only one of them to expand, and that's already a good one. Let's take a look at this next example here. So I have the same beginning index, but I have different end indices, which means that I cannot apply one of the above laws directly. I'm going to have to do something about the fact that the 5 and the 4 are not the same. So what we're going to do here is use one of the massaging techniques that we have seen earlier on, where I can take this sum and separate out the last term, therefore bringing the final index down to 4. So my sum will become from 0 to 4 of 7j cubed, but I've separated the last term, so I still have to include it. So if I plug 5 in here, I'm going to get 7 times 5 cubed. And that is the last term of this summation that I'm now separating out. And then I'm going to keep my second sum as is. Now, the good news is that once I've done that, these two summations have the same beginning and end indices, so they can in fact be put together. And the way that we put these together is exactly the same as we did in the previous question. So I'm going to skip a step and write down the final answer for this one here. It's going to be between 0 and 4 of 6j cubed. But don't forget that this extra right here belongs to the outside of the sum to be added separately. Now, what happens if we start working with products? Now, notice that I'm actually subtracting the products here, so there are no rules that allow me to intermix product and summation, so I'm going to have to be very vigilant about what's going on here. And in fact, what I'm going to do, because that's the only thing I can do, is just expand these out. So it's the product between 0 and 5 of the terms that look like this. So my first term is going to be 7 times 0 cubed. My second term is going to be 7 times 1 cubed, 7 times 2 cubed, and so on, all the way up to 7 times 5 cubed. Minus, and then I can subtract out this product. But again, because I'm subtracting, there's no way to put these together. The best I can do is just write out what is in there. So going from the index of 0 to 5, of cubes, I have 0 cubed, 1 cubed, all the way up until 5 cubed. Now, the nice thing about products is if a 0 appears anywhere, then the whole thing is 0. So there's a 0 cube here, and I should have noticed that in the beginning, and I didn't even have to write all of it out, but just for completeness. And the same thing here, right? So all of this is 0, all of this is 0, therefore the total result is going to be 0. Now, this is precisely why the next question has j equals 1. So write out the same thing using 1. We're obviously not going to get a 0. In fact, I can be extremely lazy and just copy over the portions of the product that start with 1, which also highlights the fact that these products are kind of like nested dolls, right? Like I can start with the later index, and that means that I'm only taking out a part of the product. Now, this is not going to be, I can't do this in my head, and you can plug this into your calculator or not. That's totally fine. This can stay as a number. The one thing to notice, though, is that in the sums, I can take the constant out. In the product, this constant will appear as a factor every single time, which means that it actually, if you want to simplify it, 7 here will appear 5 times. So altogether, this will be 7 to the power 5, and then followed up by some of the other numbers. Okay. Finally, I have 2 products connected with a product. So I hope to be using the law that looks like this. But I cannot do so directly yet because I don't have the same ending indices. So before I can apply that law, I have to figure out how to separate the final index. So as with the massaging the sums, you can massage the products the same way. I'm going to take this product and pull out the last term. So what's the last term? The last term is going to be 7 times 5 cubed. And then the product can carry on from 1 to 4 of 7j cubed. And then my second product, I never changed. J from 1 to 4 of j cubed. Once I've done that, I can put 2 of these products together as per the simplification in one of the rules above. So don't forget that I am keeping my coefficient here, and then I have a product from 1 to 4. And what the rule says is I'm just going to multiply the insides. So 7j cubed times j cubed. Now, of course, I can simplify that a little bit further because j cubed times j cubed, I can combine the powers. So altogether, I'm going to have 7 times j to the power 6. Okay. One thing I encourage you to do is actually take a look at these last 2 examples and try to figure out how you can put these 7s out together, pull them out using this law. See what kind of power of the 7 you have out there for additional practice and also for remembering how to do this number of elements in the list calculations.